I expect to post the key for quiz 3 late this afternoon. Still got a couple of folks to deal with this. Just to remind you, special quiz 2 due Tuesday of week coming, given that we gave you a week extension, and exam 3 is next week. Usual time slot, usual location. And as per past exams, anybody with a legitimate conflict needs to give me a note with the intention that you, with the conflict, will take the exam earlier in the day. But I need a note in order that I shall know about this. So we proceed with the nuts and bolts of fundamental electrochemical considerations. How to develop, derive equations for half reactions. Because the way to develop equations for redox reactions based on the chemistry of the system is to take the system apart, the redox reaction system apart, into its oxidation half and its reduction half. Then we couple the halves and we get the equation for the net redox reaction. To achieve this, we provided a bunch of rules. Learn the rules. In so doing, you will see, as we have already reminded you, that in the main, these rules depend on Bronsted-Lowry acid-base chemistry. So back to chapter 18. Question 2211. Let's imagine we're running a reaction in basic aqueous solution. Basic solution. And species during the course of this reaction become protonated. That means H pluses have got to come from someplace. From where do the H pluses come? What's the answer that's always correct? I heard water. That's not correct. The strongest acid present at high concentration in the system. Because the system is basic, does that guarantee the strongest acid present in high concentration is water? Let's have an example of a system which is obviously basic and yet contains an acid which is stronger than water and present at high concentration. How about ammonium-ion ammonia buffer? You betcha. And there are a bunch of other examples we could get from the information on the acid-base table, where the strength of the base is greater than the strength of the acid. The ability of the base to snag H plus exceeds the ability of the conjugate acid of that base to provide H plus. Any acid with a Ka value that's less than what value, what number will fit this bill? Any acid with a Ka value that's lower than what number? 1.0 times 10 to the minus 7. That's right. Because if an acid has a Ka value of 1.0 times less than 1.0 times 10 to the minus 7, that's a flat guarantee that its conjugate base will have a Kb value that exceeds 1.0 times 10 to the minus 7. How about that? Now then, 2211. Electrolysis, that's what this symbol stands for, omega. When you see this, it means we're talking about an electrolysis process. We're going to electrolyze 1 molar sulfuric acid solution. In so doing, we will observe the development, the production of oxygen gas at the anode, the electrode at which oxidation occurs. What's the half reaction for this process? From what material component of the system do we get the oxygen atoms necessary to synthesize the oxygen molecule? Well, as usual, as always, what do we start with? PSI. You don't know what's in the system, you can never answer a question like this. But we've learned about this. There's our PSI for the sulfuric acid solution, 1 molar. Each of these principal species contain oxygen as a component atom. From which of these species will we get the oxygen atoms? By oxidation to make molecular oxygen. What do you think? Well, let's start by taking a look at an OH bond and its strength compared to an SO bond and its strength in this dihydrogen sulfate ion. Which of these bonds do you think is stronger and why? Now notice, to get this oxygen atom, you'd have to break an OH bond as well as an OS bond. So we'll rule out that oxygen. What about the other 3 oxygens? Are the bonds of those other 3 oxygens to sulfur stabilized by resonance? You betcha. That makes them strong, doesn't it? Stronger than an SO single bond. Now then, tell me, for this hydrogen sulfate ion, what's the oxidation state of central sulfur atom? Central atom sulfur? +6. Do you think, based on oxidation state assessment, it's reasonable to conclude that stripping a -2 oxidation state oxygen from a +6 oxidation state sulfur might be tough? Coulomb, you think that might be tough? You're damn right. So from this we'll conclude our oxygen atoms to make the O2 molecule will come from water or hydronium ion. Now what's your choice? Simple, fundamental thermodynamics is all you need to consider to answer this question. If I'm going to take a hydronium ion and rip it up to make available an oxygen atom, ultimately to make an oxygen molecule, how many OH bonds do I have to break? 3. But if I'm going to do that here? 2. So do you think this is a better bet? Absolutely. So let's see with this information if we can write the half reaction. We're kind of crowded up there, so we'll write this down here. We'll start with this. We've recognized water to be our oxygen atom source, and we know this is an oxidation process because in the water molecule, the oxygen atom oxidation state's -2, but 0 in the oxygen molecule. So clearly this is an electron liberating half reaction, an oxidation process. How many of these do I need to tear up to give me enough O atoms to make this?
2.
Good. Now when I tear this up, how am I tearing it up? How am I breaking these bonds? Am I breaking the bond here, here, or here? Huh? Which atom is more electronegative? Good. So I'm breaking the bonds like this. The electrical energy supplied will take the electrons away. Now then, if I break the bonds like this, beside making available oxygens, immediately -2 oxidation state oxygens, but I'm also making available to putting in the system what? H+, right? What will consume H+ in this system? What consumes H plus in every system? No. The strongest base present in high concentration. Now let's look at the PSI. For this system, the answer is water. But keep in mind, H plus in any system always comes from the strongest acid present in high concentration, which you determine by examining what property of the system? PSI. H plus consumption will always be done by the strongest base in the system at high concentration. How do we determine such? Examine the PSI. How about that? Old term we're using this. If you don't know what's in the system, you cannot deal with the chemistry of the system. But when you know what's in the system, you have now every opportunity to deal correctly with the chemistry of the system. If these damn stupid general chemistry textbooks would ever learn this, they might get someplace in trying to communicate this wonderful science to you folks. Now then, we've recognized we've got to rip up 2 water molecules to give me enough oxygen atoms to make one of these. In so doing, I'm putting how many moles of protons in the system? 4. And what is going to consume these protons? Water. So how many more waters do I need? As I rip up 2 water molecules to make my oxygen atoms available, from which to synthesize my oxygen molecule, I'm putting 4 moles of H plus in the system, right? So I need 4 moles of my strongest base to eat up these H pluses, don't I? And that means, since I've recognized water to be this strongest base, how many more waters do I need? 4. How about that? So let's go back to the coefficient on water and adjust it to 6. And recognize that when water consumes H plus, what do I make? I make hydronium ion, don't I? And with this, I've paid attention to every material component of the system, so I have a statement which shows material balance. So now I must establish charge balance. No charge, 4 plus, 4 moles of electrons liberated. Does that not keep with total change in oxidation state? Did I not take 2 minus 2 oxidation state oxygens and turn them into 0 oxidation state oxygens to make my oxygen molecule? Isn't that 4 moles of electricity liberated? Bingo. Now then, this half reaction produces hydronium ion. Yet it is true, as this electrolysis process runs, pH remains fixed. pH does not decrease. How can this be? Well, let's ask a fundamental question. Have we as yet paid attention to all the chemistry which is occurring in this system as oxygen is produced at the anode? No. What have we not yet paid attention to? What have we not yet considered? The basic properties of oxygen. What have we not yet considered? Can we run a half reaction by itself? No. Can we only oxidize oxygen and that's the only thing that happens in this system? No. We've not yet paid attention to what happens at the cathode, have we? Well, then let's do that. So what I want to do now is to answer the question, as this electrolysis procedure goes on, what eats the electrons? What will eat the electrons in any chemical system? The strongest? Nope. Nope. Tell me, by definition, what is an electron consumer? It's known as an oxidizer, isn't it? Just like an electron liberator is known as a reducer. More language, right? In this system, what is the strongest oxidizer present in high concentration? There's the PSI. Keep in mind we've done this. We put zinc in pH 7 water and observed nothing to happen, right? Yet when we put zinc in pH 0 water, a reaction took place. Because we discovered that hydronium ion is not only a stronger acid than water, it's also a stronger oxidizer. You betcha. Did we not recognize that the production of hydrogen by redox depends on pH? You betcha. So what are we looking for? In this system, we're looking for the best acid. That's hydronium ion, because that's our best oxidizer. And by way of what we've done previously, when hydronium ion functions as an oxidizer, to what does hydronium ion get reduced? What does hydronium ion get reduced to? Hydroxide is not a reduction. That's an acid-base transformation. When I reduce hydronium ion, what do I produce? What did I produce when zinc reduced hydronium ion? What did I make? Zinc reduced hydronium ion. What did we produce? Did we see bubbles? What were the bubbles? What were the bubbles? Hydrogen. So I'm stripping +1 oxidation state hydrogen atoms from the hydronium ion, and in so doing I blast each one with an electron. That turns it into an H atom, and I need to kill therefore 2 hydronium ions to make me an H2 molecule, don't I? Okay, so far? Have I got material balance? Have I paid attention to every material component of this half reaction which shows reduction of hydronium ion? So to establish this as an equation, I need to establish charge balance. What's my electron multiplier? 2. And now, if we're going to write a net redox reaction, what is the last step in this process? We have to couple the half reactions, don't we? And if I'm going to couple these two, what do I have to do this half reaction? Multiply it by 2 to show the consumption of 4 moles total of electricity, given that this half, as written, liberates 4 moles of electricity. Well, that means how many moles of hydronium ion consumed? 4. How many moles of hydronium ion produced? Any net change in hydronium ion molarity? pH stays the same, doesn't it? How about that? All right. So we go to page 2213. We will consider the oxidation of chloride ion to chlorate ion, ClO3-, occurring in strongly basic solution, 1 molar sodium hydroxide solution. Now, since we finished with this, I'll get this part out of the way. And start with this. Have we not recognized that chloride ion is getting oxidized even if we didn't have oxidation here? And we said we're looking at a redox reaction in which chloride ion is converted to chlorate ion. Would you recognize at a glance that this has got to be oxidation of chloride ion? Because for the chloride ion, what's the oxidation state of chlorine? -1. Here? +5. Isn't this oxidation? Absolutely. So we'll write this. Now I need -2 oxidation state oxygens. Again, except that in this case the -2 oxidation state oxygens are not going to get oxidized as they did in the electrolysis of sulfuric acid system. Here, chloride ions getting oxidized. Nevertheless, I still need -2 oxidation state oxygens. Where am I getting them? We're running this in 1 molar sodium hydroxide solution. There's my choice list. Am I getting my -2 oxidation state oxygens from this or from this? I'm listening. If I want a -2 oxidation state oxygen, how many bonds I got to break here? And it's breaking the same bond, isn't it? And breaking the same bond the same way. So which is cheaper? This one, isn't it? So guess what? We're now seeing how redox chemistry provokes hydroxide ion to behave as what kind of species? How are we tearing up this hydroxide ion? Tearing it up like that, aren't we? So beside making available oxide ion by this bond-breaking process, what else are we putting in the system? So guess what redox chemistry is capable of doing? Makes hydroxide ion behave as what? What? A Bronsted acid. How about that? Have we seen cases during acid-base chemistry and semi-soluble salt chemistry where hydroxide ion was provoked to behave as a Bronsted acid? Did we see cases, acid-base chemistry, semi-soluble salt chemistry, where hydroxide ion was caused to behave as a Bronsted acid? Did we see any such cases? Did you see any such cases with your work in laboratory? Yes. What cases have you seen? Have you seen this? Does this reaction involve hydroxide ion not only behaving as an oxide source, but as an H+ source? How about that? We've seen this before. You can do a lot of marvelous things with chemistry, as long as you keep your eyes open and the best computer you got whirring at all times. How many hydroxide ions do I need to chop up? I need 3 of these -2 oxidation state oxygen to make one of these, don't I? So we'll start with this. Is that going to be the right multiplier on hydroxide ion? Yes or no? No. Why not? Why is 3 not the correct coefficient for hydroxide ion in this half reaction? Because not only does this ripping up of 3 hydroxide ions make available our 3 -2 oxidation state oxygens, which glue onto the chloride ion to make this. This process also puts how many moles of H+ into the system? 3. And what's going to consume H plus in this or any system? The strongest base present in high concentration. Don't ever say anything else than that. And now let's go back and look at the inventory. Tell me in this system what's the strongest base present at high concentration? Hydroxide ion. So how many moles of hydroxide ion more do I need? How about that? Bingo. So beside chlorate ion, what else am I making? How much water? 3. Good. And now we have material balance for this half reaction, because we paid attention to each material component of this half reaction system. But I still don't have an equation, do I? I'll have an equation after I establish charge balance. What's the electron multiplier? Does that keep with net change in oxidation state? Chloride ion, -1. Chlorine atom, +5. If I go from -1 to +5, do I have to get rid of 6 moles of electricity? How about that? Now then, let's imagine we ran this oxidation not in 1 molar sodium hydroxide, but instead in ammonia solution. So now the strongest base present in high concentration in our system is ammonia. So now what will be my source of the -2 oxidation state oxygens? Water. How many waters do I need to murder?
3.
And how am I murdering these waters? Like this. So as I murder these waters to make available 3 -2 oxidation state oxygens, what else am I putting in the system? 6 moles of H plus. What's going to eat these 6 moles of H plus? Are these guys now recognized as the best base in the pot at high concentration? So how many moles of ammonia do I need? So now, what will be my additional product? You know what happens when ammonia gobbles up H plus. How many?
6.
Done. Now, let's go to 2215. 2215, as you see, is a battery of considerations regarding development of half reactions, and in some cases we ask you to put them together, the half reactions for the system, couple to get the net redox reaction. So let's go to 2216. I mean 15, pardon me. Starting with this. If I tell you that the R product is NO gas, can you quick and fast write down the equation for the half reaction? that shows by reduction the production of NO gas? Have we developed this half reaction previously?
Yes.
When did we develop this half reaction? Did we not recognize that when copper metal was oxidized by 6 molar nitric acid, we made NO gas as the reduction product? Right? And the half reaction was 4 moles hydronium ion plus nitrate ion, because if you're making NO, you've got to reduce nitrate ion. It's the only nitrogen-containing thing in the pot. Plus question mark electrons becomes 6 waters and 1 NO. Sound familiar? What does question mark get replaced by? What's the electron multiplier for this half reaction? 3, isn't it? Because in nitrate ion, the oxidation state of nitrogen is how much? Plus. And in NO? Plus 2. Done. Silver simply becomes silver plus, as shown in the half reaction table 2 in the notes. Now then, let's change the oxidizing system, but not change the reduction product. Now we're going to oxidize silver. Rather than straight nitric acid solution, we're going to consider oxidizing silver in aqua regia, the water of royalty. Why is aqua regia called the water of royalty? Why is it the water of royalty? Aqua, water. Regia, royalty. Dissolve gold. Oh my. You think gold is a metal of royalty? Silver? Platinum? You betcha. Aqua regia is such a strong oxidizing system that it's capable of oxidizing metals which are notoriously poor reducers. Extremely stable, unreactive metals. Gold, silver, platinum. Now we've already recognized 6 molar nitric acid will oxidize silver. But 6 molar nitric acid will not touch platinum, will not touch gold. But aqua regia will. The difference lies in coordination chemistry. Because in order to get gold to be oxidized by nitric acid solution, we have to put in a high concentration of chloride ion so that we can complex gold as it is oxidized and create a species which is a hell of a lot more stable than gold ion AQ. Specifically, it's tetrachloroaurate minus, what's that? It's AuCl4 minus a tetrahedral complex of gold. Well, we're not going to do that one now. We're going to do this one. We're going to oxidize silver in aqua regia, and we will still produce NO as the reduction product. The question is, if we have recognized for this half reaction that we get Ag plus AQ, when we oxidize silver in aqua regia, will it oxidize with the same electrochemical potential? Will I still make Ag plus AQ? Have you read the notes about aqua regia? How's aqua regia prepared?
Mixing H2O with oxygen.
If I send you to the laboratory and I tell you to make some aqua regia, what you going to do? Besides jump up and down and scream and say, I don't know. In which case I invite you to leave. That's right. You make a mix of conch nitric with conch hydrochloric acid solutions. So now when we look at our PSI, beside hydronium ion and nitrate ion and water, what else we got in there? Chloride ion. Didn't we remind you a moment ago about the ability of Aqua Regia to oxidize gold, whereas 6 molar nitric alone won't oxidize gold because you need the additional thermodynamic boost of complexing gold as it's oxidized by chloride ion? So I ask again, if I oxidize silver in Aqua Regia, will this redox reaction run with the same electrochemical potential as oxidizing silver in nitric acid solution? And the answer depends on whether or not I still get silver ion as my product. Because if I get silver ion in my product, I'm going to have exactly the same potential for the redox reaction because I'll have exactly the same redox reaction. What am I going to make as my product in this system? What will I make? I'm oxidizing silver to the +1 oxidation state. What's my product going to be? Is it silver ion AQ? What is it? Silver chloride. Tell me. Look at the half reaction table. By what change, by what amount does the electrochemical potential change when I conduct the oxidation of silver in Aqua Regia rather than straight nitric acid solution? Ag goes to Ag plus electron. Are you seeing minus 0.80 volts? Are you looking at the half reaction table? Do you see that? But if instead I oxidize silver in the presence of chloride ion to make silver chloride, what's the electrochemical potential? Minus 0.22 volts, isn't it? Didn't I up the potential by about 0.6 volts? You betcha. Because silver chloride is a heck of a lot more stable thermodynamically than silver ion. Keep in mind that among other things, this half reaction table is mainly a table of thermodynamic stability information. Silver chloride, a lot more stable than silver ion. All right, we go to number 3. Zinc. I observe if I run this redox reaction that if I oxidize zinc with 6 molar nitric acid solution, I'll make nitrogen gas. Based on this information, is it a fair statement that zinc is a stronger reducer than silver? Based on the information we have on the board, is it a fair conclusion that zinc is a stronger reducer than silver? Yes. Why? When silver reduced nitrate ion in acid solution, I got NO, didn't I? When zinc does the job, I get nitrogen. In which case, in the same system, but with a different reducer, have I provoked a much greater change in oxidation state? Zinc. All right? Let's put that one on the board. Now let's do this redox reaction with magnesium as the reducer. Now I make ammonium ion as my redox my reduction product. How does the reducer strength of magnesium compare to that of zinc? How does the reducer strength of magnesium compare to that of zinc? Even greater yet, isn't it? Stronger yet. Now what kind of change in oxidation state did I produce? +5 nitrogen and nitrate ion all the way to -3 in the ammonium ion. How about that? Now then, half reaction. Clearly, if I'm making nitrogen as my reduction product, I've got to be murdering nitrate ion, don't I? So right off the bat, I'll start with this. Because if I need to kill nitrate ion to get nitrogen atoms to make a nitrogen molecule, I got to kill 2 nitrate ions, don't I? Otherwise, I won't have enough nitrogen atoms. And when I kill the nitrate ions, I'm stripping away all the peripheral oxygen atoms, am I not? And I'm stripping them all away as an oxygen atom in what oxidation state? -2 and -2 oxygen. From an acid-base standpoint is known as the oxide ion and is found on our acid-base table as the strongest base present on the damn table. How about that? So as I murder 2 nitrate ions to make available my necessary quantity of nitrogen atoms from which to synthesize my nitrogen molecule, I'm also putting 6 moles of oxide ion into the pot. If I put oxide ions in any pot, with what will they react? The strongest acid present in high concentration. And now I pay attention to my PSI, and for this system recognize that's hydronium ion, isn't it? Wonderful. And I got to kill 6 of these oxide ions. So how many hydronium ions do I need? I'm going to clobber 6 of these. And I'm doing this in acid solution. How many hydronium ions do I need? I'm listening. I'm listening. 12. Will 6 do the job? And I'll give 1 H plus to each oxide ion and make hydroxide ion in acid solution? Kaput! Not making any bases in acid solution. And you can take it from there. Try this one too for your own practice. Same idea. And now, 4. Once again, because of coordination chemistry. Well, I shouldn't say once again, but let's say because of coordination chemistry, I'm now finding that oftentimes metals can be strong reducers in basic solution, not just acid solution. Because in basic solution, many oxidized metals complex with hydroxide ion or precipitate with hydroxide ion. And such materials are thermodynamically more stable than the hydrated version of that metal ion. It's all thermodynamic stability. So in this case, we're saying if we oxidize aluminum in concentrated sodium hydroxide solution, 6 molar, my oxidation product is this, which for simplicity's sake we call the aluminate ion. You've seen this in laboratory, haven't you? Question: what is the correct net half reaction for this oxidation process? I ask this because for reasons I cannot understand, I've seen many students have great difficulty with developing this half reaction equation. And the only conclusion I can reach is that those students who have difficulty in developing this half reaction equation have forgotten that if you're going to write equations for any chemical system, what system property do you have to pay attention to always? It's called PSI, isn't it? Is this system rich in hydroxide ion? Is this system rich in water molecules? So I say, what the heck is hard about this? Doesn't that give me what I need to make that? Absolutely. And 3 is my electron multiplier, which keeps with the fact that the only positive oxidation state aluminum ever shows in its chemistry is +3. Pick it up from this point next time.